Now, on to tonight's presentations. We have three speakers that are going to present energy efficiency research and new process integration in the Canadian pulp and paper industry, as well as the transformation that the industry has undergone in Sweden. I ask you that you please keep your questions for the period reserved to that end after the three presentations. Let us now introduce the first speaker. Professor Jean Paris has more than 45 years of experience of R&D management in industry and university. He studied at the University of Nancy in France and at Northwestern University in the US, and then worked at Procter & Gamble in the USA and Europe. He has been at Polytechnique, Montréal since 1976, where he joined the efforts of Paprika and then FBI Innovations in support of the Canadian pulp and paper industry. He created the research center on this subject at Polytechnique in '95 and was its director until 2006. He continues very involved in expanding his activities in the field. In fact, he is the co-author or author of more than 500 publications on the topic and contributed to the training of dozens of master's and PhD students. And today he will tell us about improving the thermal energy efficiency of the pulp and paper industry. Jean.
Very nice, but somewhat inflated introduction, and it will be hard to follow by a presentation which will match the grandeur of the presentation. I'll do my best. All right, so our subject is improving the thermal energy efficiency of the pulp and paper industry. This work has been done primarily with two students, Radia Amaha and Mohamed Kishka. Radia Amaha is still with us, and she is becoming a postdoctoral fellow. Mohamed has left several years ago, and he is working in the energy industry in Alberta. So the main subjects of my presentation is divided in two parts. First, the context and the justification of the energy enhancement of the pulp and paper industry. This industry is in difficult times, and the forest biomass is a feedstock, a very appropriate feedstock for new products. The industry is diversifying its portfolio of products. The second part will be on the methodology itself that we have developed. There are challenges to be confronted, so we have developed this novel methodology, and I will present the results and further development. So the industry, as was said in the industry, the pulp and paper industry in Canada has been traversing a difficult period for some time. And one reason is that the demand for commodity products, newsprint, printing and writing paper, is declining, and we all know why. It's because of the iPads that you are working with now instead of working on paper. And another reason, though, is also that there are new and large pulp making facilities coming online in a region with fast-growing forest and low labor costs, for example, in Brazil. And trees grow much faster in those regions, and we cannot compete with that. So if it is managed and exploited responsibly, the forest biomass has a net zero carbon footprint. That is, the carbon which is absorbed by the new growing biomass is superior or equal to the CO2 which is generated by the conversion and utilization of wood. So the net balance can be nil. Forests have also the advantage not to compete with food crops for arable lands. It grows generally on marginal land, which is an advantage, a point important. The forest and the pulp and paper sectors have solid well-implemented infrastructure and a trained and competent workforce. Existing paper mills can process and partition the forest biomass to manufacture new products, and we will see that a bit later. Well, what kind of product can be manufactured? The three main components of wood are cellulose, hemicellulose, lignin. They are all in the range of 30 to 35%, depending on the species of wood, of tree, the type of tree, and the climate and the soil. We have concentrated our work on the hemicelluloses and lignin. Hemicellulose is a very complex polymer of sugars, of C5 and C6 sugars, and therefore they can lead to the sugar platform where there is abundant opportunities for manufacturing product. The Kraft black liquor is the lignin, I'm sorry, is a phenolic compound which is very complex, and it can be also the door to the phenolic platform of chemicals. Finally, the extractives are small concentration products of a great variety, but they can also be used and transformed in specialty high-value products. We will discuss hemicellulose and lignin. Now, the concept of integrated biorefinery consists in building a biorefinery, which is a process in which a component of the wood biomass is transformed in a new product, to build it on the site of a pulp and paper mill, and to integrate the two so that the needs in energy, water, steam, and in raw materials is supplied to the biorefinery by the paper mill. Now, here is an example. I have here the yellow line is a very simplified schematic of the Kraft pulping process. First, there is chemical delignification of the wood, washing, bleaching, drying, and it gives a pulp. Here we are dealing with mills that make dissolving pulp, which is a high purity pulp used as a chemical precursor, for example, for rayon and cellophane and other places. It's not used for paper, and the interest for us is that a part of the hemicelluloses is removed at the beginning and then reintroduced later. Here, I think I have gone too fast, but that's all right. Here, there is hydrolysis of the hemicellulose to purify the pulp, and it's re-injected to be burnt, concentrated in burnt in the recovery boiler of the Kraft process. So what we can do is take part of this, or here it looks like we would take all, and transform it into a biorefinery. Another thing that we can do from the Kraft pulping process is derive some of the black liquor and extract the lignin which is in it and which is normally burned into the recovery boiler. And this lignin is directed to a biorefinery plant. Now, this is an example of a process for furfural making from the pre-hydrolysis derived from the Kraft process, and how it is transformed. First of all, it is concentrated because the stream that we get is very diluted in water. Then the sugar is converted in furfural, and then there is the bigger part of the plant is, you see at the end, the concentration and the purification of the furfural. It's done by a sequence of two to distillation. This is a very frequent process in the chemical industry when you have a product which forms an azeotrope. To go over the azeotrope and supply it at a high concentration, you need to do two distillations which are connected in a special way. So this is one of the processes that we have developed. We have developed many others. Okay. So the integrated forest biorefinery may be a very effective way for the pulp and paper industry to expand its product portfolio and penetrate new markets. It must, however, reduce or eliminate fossil fuel consumption, which generally is natural gas, by energy intensification to reduce its operating cost and the emission of greenhouse gases. And that's really the core of my presentation. We have developed a new methodology to analyze and enhance the thermal energy efficiency of kraft pulping mills. And we have validated in 3 actual Canadian mills in operation. All right, I'll never master this thing. Okay? All right. So the main points of this methodology, it's not, you know, a fancy optimization mathematical type of thing. It's practical. It's a practical stepwise project-oriented procedure. It combines steam and water, very important, because in a kraft process and in a biorefinery, they are water-based products, and therefore water is also a vehicle for energy. We use heuristics, and I'll come back to that. And of course, the work is supported by a simulation of the process. Now, one of the methods that we have used, but it's not really very important in the project, is the conventional thermal pinch analysis. I'm sure that most of you know what it is. You see, we have, in a process, we have some streams which must be cooled. So they are the hot streams from which we must remove heat. And then there are other streams which must be warmed. So we form 2 composite curves, one of the hot streams and one of the cold stream, and we try to bring them as close as possible, but there must always be an interval between the 2 so that the exchange is done, and then a part of the heat needed by the cold stream can be supplied by the hot one, but at both ends there is a region where there cannot be exchanges, and this gives you the minimum heating requirement at the right end and the minimum cooling requirement. This is a classic, and we thought that maybe we could even do better. Good. Now, in a process such as the pulping process, the pulp and paper process, which are water-based, there is also a lot of heat transported by water. So the method called water pinch, which is the same idea as for heat, but the representation is not the same. Here you see the pure streams and the more the sources of water, which are the horizontal lines at the top, and the need for water, which are the sinks. The bottom lines are horizontal, and they form not ladders but stairs. So when you bring the 2 stairs to bump into each other, that gives you the maximum water that you can use from what is already in your process, and at the other end you have the minimum waste water produced and the minimum fresh water required. Now, the interest of the water analysis, water stream analysis, is that we have the water and purity, which is the diagram I showed before, but also their temperature vary. And this gives us some opportunities for additional benefit. Here it is. Here I have combined at the top the first diagram with the two composite water curves, and at the bottom I have the representation of the heat contained by those streams, and therefore how much heat can be gained by the sources or lost by the sources. So this is a combined heat and matter type of analysis derived from the what was I saying? Okay, so there is a limitation for both of those analyses, is that they take into account streams which are in the process, which are already there, and they try to improve the exchanges between the streams, but they do not create new connections, and therefore they ignore a certain number of exchanges in a process, such as cooling by mixing and diluting, and simultaneous heat and water exchanges. So we have to do it iteratively between water and heat, but we also have to extend it to other processes. Here is a kind of a schematic diagram of the type of exchanges, energy exchanges that occur in a plant. Now the bubble at the center is thermal pinch analysis. The yellow bubble is water pinch analysis, but we have also to take into account mixing. There is a lot of stream mixing in a pulp mill, which are not treated by the two previous methods. And there is a lot also of condensate that can be reutilized, so that we have a lozenge here. A lozenge, and when we have optimized that, we have the possibility to upgrade energy by using a pump, a heat pump, or to convert energy into a heat and power unit. So we must consider all of that. So we have developed a method, a stepwise method, which has those steps here. First, developing a database, of course, which is a simulation of the process. We'll come back to each of those methods. Then we have pre-benchmarking, which is evaluate the state of the process as it is before we do anything. Then we have the core of our methodology is energy in form of water of steam systems analysis, the steam and water efficiency enhancement. This leads to retrofit heat exchanger network design, and finally post-benchmarking, which is comparing the end to the beginning. So I'm going to develop this, those parts, which is really what is new in our methodology. I will come back to step 1 and step 2 because we are continuing our work and we are doing development here. So the method is based on the application of heuristics to the process to improve it. Now, there is nothing secret to heuristics. Here is cascading countercurrent water flow together. And when we go in a mill and study in depth the process, we feel that this simple way to improve the process is not very much used. And it's the same for the other heuristics. Give priority to water streams with higher flow rate. That's obvious that you should do that. Well, you'd be surprised. It's not always done. Then there is high temperature water streams are preferably, when you can use them, than steam streams, because it costs less to produce hot water than to produce steam. And finally, that's also something which is often done. For practical transport and pumping reasons, people have had the tendency to gather streams together. But here, some of those streams are fatally diluted. So this is not a good idea either. Now, once we have looked at the process with that on mind, because that's what we do, it's very practical, very processed, not high mathematics or optimization techniques. I want to underscore that. Then we redo the heat exchanger network. And the process, the methodology is shown here, targeting the temperatures, that is determining the temperature in and out of the network, of the heat exchanger, data extraction, then design using Aspen. I presume that many of you have used Aspen plus the software, which is, I think, very frequently used by the process industry and engineering industry to design processes. Then we look at, we evaluate the results in terms of heat sources available, and we can reiterate until we have a new design. Now, here are results. You see, this is a diagram of the hot and warm water network of a kraft mill before we have done anything. I'm not going to explain to you in detail what is it. That's not the point. It's just that, see, we start with a photograph. That's the hot and warm water network. And then, by the methods, the techniques that I have talked about before, we look at how we could improve that, and here is the results. You see that we have very much simplified the network and reduced the number of heat exchangers. It has gone from 5 to 4, which is a decrease of 25% incidentally. And that's a very simple part, a small part of the mill. Some of the diagrams that we have developed, the students have developed, I must say, for this project are huge compared to that, 3 or 4 times the same this time. So, here are the results. Very interesting. So I told you at the beginning, and you must remember, you may remember that we did it for 3 kraft mills. And here we have the results presented as 4 bars. Well, the reason is that, so let me explain. The one on the left, the blue, is what we call mill A. The one of the right, violet, is mill C, and in between we have mill A in 2 configurations. It can be, with the savings that we do, the reduction of steam consumption, but the equipment is still there to produce the steam. So the question is, what can we do with the steam? So we can sell the steam, or we can drive a cogeneration unit. So you see that another point which is very interesting that this diagram shows is that there is a great difference from mill to mill. Here, mill B, the one with the 2 bars in the middle, has done a pretty good job until now in water management and in steam management. The 2 others are not as good. Now, but this gives you percent of water saving. You see that we can go to about 25 to 50 in one of the mills. by just doing, you see, rearrangement of the process, as I explained earlier, then we reduced the steam consumption, but the equipment is still there. The boilers are still there. So we have liberated steam production capacity, and that gives us the opportunity to do some other things, such as electricity generation. But before we do that, what we have done is eliminate fossil fuel. So natural gas, there is no more natural gas in the mills here. And this is a big saving, which is reflected at the fourth bunch of bar charts. The third one is the cost. Of course, it costs money to improve the mill. And we have it's in the millions. But considering that the benefits from not having to buy natural gas and producing electricity or selling steam, we increase the profit of the mill, so that at the end, and that's the criterion that the mill people will look, the payback time is fairly reasonable. Actually, it's quite short in one case. The mills will consider up to 2.5 years to, I may be contradicted by a colleague and former student, Enrique Mateos later. He's working in practical things at FPI, but the 3.1 year would be considered as maybe not in the current economic climate, but the 0.9, it's a must, you must do it, and the 1.8 to 2.1 are in between. Probably it would be done. So now coming back to the beginning, this is still in progress. In other words, we are improving those two steps. So the database is essentially a simulation of the operating plant as it is, and we use the qu'a platform, which is a software broadly used by the pulp and paper industry in Canada. So we archive from, there are lots of instruments that make measurements constantly in a mill, and they are stored in software. It's called the virtual private network, which I think is a nice expression. And we were given access to this very private network, but we had the students, I say this was done mainly by students. They went to the control room of the mills and copied the values of the parameters, and those values change all the time. Not necessarily very much, but they vibrate. They vibrate. So that, you cannot, for sure you cannot read everything at the same time, and it doesn't give you, if you just read one value in other places, it will not give you congruent heat and mass balances. So we made lots of readings, and then we apply a process which is called a reconciliation of the data. And when we do that, we observe sometimes that there are points which are clearly out of range. So we have observed there an equipment which doesn't work, and we can correct it eventually. So after we have done that, we have a simulation which represents a long-term steady state average, and we have heat and mass balance which is coherent, which form a working ensemble for the whole mill. The second step of my method that I showed earlier is equipment performance analysis. This is To do that, we characterize the equipment by what are called key performance indicators. And you go industry and people will know pretty much, what it is. But we have been looking here, we have used exergy. Now, that is a novelty in the pulp and paper industry. But exergy is really a powerful tool to analyze the heat processes. So we have developed key performance indicators based on exergy. And this has given us some more power in analysis. So I arrive in my conclusion. A systematic methodology for the energy efficiency enhancement of water-based processes has been developed and incorporates innovative techniques, or we think innovatives, which are combined water and energy analysis, heat exchanger network retrofit design, and here I have put in italic the two things that I was just discussing about, the first steps, reconciling database and KPIs based on exergy. The project, the method is project-oriented, supported by heuristics, very simple, good sense things, and the current version focuses on craft processes. It could be generalized, we hope it can be generalized to other water-based processes. So, finally, the methodology has been applied to operating craft pulping mills and produced results which are very impressive and interesting, beyond what is normally done by usual engineering methodology. And in its current state of development, it is operational and validated. Work is envisaged to develop portable computer-aided versions. So what characterizes the method is rigorous analysis, heuristic rules, project-oriented, and that's the end of my presentation. I thank you very much.